So, we have seen how binomial coefficients can be arranged inside a triangle called Pascal's triangle. In this lecture, I am just going to do a little exploration of which binomial coefficients are even and which are odd, how many are even, how many are odd, and so on. So, let us just draw Pascal's triangle once again with the even and odd binomial coefficients. So, what I am going to do is I am going to write the odd binomial coefficients in red. So, we start with the 0th row of Pascal's triangle. Remember, the nth row of Pascal's triangle has n choose 0, n choose 1 up to n choose k. And so, the first row is 1 1, both are odd. In the third row or rather row number 2, n choose 0 is 1, n choose 2 choose 0 is 1, 2 choose 1, well it is 1 plus 1. So, that is 2, that is even, and then we have 1. The next row it is 1 3 3 1, a nice picture is emerging here. Let us see what happens next. So, next row, always the row starts with 1 which is even, and now what do we have? After that we have 4, 3 plus 3 is 6 which is even, 3 plus 1 is 4 which is again even, and then we have 1. And let us just do a few more rows. So, what happens after this? So, 1 5, but then we have 10, and then we have again 10, 5 which is odd, and 1. Then we have 1, 6, 15, what comes here? 20, very good, 15, 6, 1, and so on. Actually, this process is getting a bit cumbersome. Let me do this again, but we only need to keep track of whether numbers are even or odd. We do not need to remember the actual number. It does not matter if this was 10 or whether it was 12 or whatever. This number here is even, this number here is even, even plus even is even. This 5 here is odd, this 10 here is even, even plus odd is odd. So, we can just do this whole thing modulo 2. So, let me just do this once again, and I will be able to do it much faster, as you will see. So, we will just keep write zeros and ones. Whenever something is odd, we will write 1, when something is even, we will write 0, and I will write the zeros in blue. So, 1 plus 1 is 0 mod 2. So, we will do everything mod 2. 1 plus 0 is 1, 1, 1, and then the next row it is 1, and then 1 plus 1 is 0, 1 plus 1 is 0, 1 plus 1 is 0, and then 1, and then we come back here, we have 1 1 0. See, this is much faster, and 1 0 1 0 1 0 1, and let me do one more row, 1 1 1 1 1 1 1. Oh, here I have used the wrong color, let us change that to red, and so on. It looks like there is a certain pattern emerging. Now, I used a computer to work out these colored triangles of zeros and ones. Here is a computer generated image of these zeros and ones. I have done binomial coefficients for n goes from 0 up to 31. There is something very interesting you will notice here. Firstly, this last row, the 31th row, everything is odd. Actually, you can see this pattern before also. Certain rows, all the numbers are odd. Which rows are these? Well, if we go back to our previous picture, we saw that, well, the 0th row everything is odd, the first row everything is odd. So, that is the row now n choose 2 choose k, this is 3 choose k, the third row n equals 3 everything is odd, n equals 7 everything is odd, and if you look at the bigger diagram here, the odd entries are 0, 1, 3, 7, 15, and down here we have 31. So, these odd the rows, so here is an observation, row for n equals 2 to the power k minus 1 is fully odd. And what about the row following an odd row? Well, if you have a row of ones, well, of course, you will always start with something odd and end with something odd, but in between you will always get zeros, right, because 1 plus 1 is 0 mod 2. So, the row following it, so row for n equals 2 to the k is almost fully even except for the first and last entry. And in fact, because this row is even, that you will be only adding zeros and you get this whole triangular region here. This whole triangular region here is going to be even, right, and we have similar triangular regions which are smaller, which are even. So, we have these regions of zeros, and every zero is in fact in one of these regions. These regions have varying sizes. And here, just for fun, is the image for n going from 0 up to 63 in fact. So, it is double of the previous image, which was n going from 0 to 32. So, what is really happening here? Can we establish the pattern that is happening? So, let me just go back to this picture I was drawing here. So, we have this region here, we have done rows 1 up to 0 up to 0, 1, 2, 3, 4, 5, 6, 7, rows 0 to 7 of odd entries in Pascal's triangle. So, let us take this piece, and now we have this triangle with all ones in the bottom row, right. What happens next? We see that in the next row there will be a 1 on the left, a 1 on the right, and this entire pattern will repeat. So, we will have a 1 here, a 1 here, and in the middle here we would have a region completely composed of zeros. And what happens at the next stage? Well, we could take the same picture again, copy it, make 2 copies of it, put 1 down here on the left, put 1 down here on the right, and in the middle we again have a region of zeros twice as large as the previous time. And we can keep doing this. Let me do it once more. And once again we have this region of zeros in the middle. And we could keep doing this indefinitely, drawing more and more of this Pascal's triangle modulo 2. There is another way of drawing this kind of a picture, and it actually comes up in the study of fractals. It is called the Sierpinski gasket. Let me show you. So, what you can do is, okay, so you start with an equilateral triangle, and what you do is you divide it into 4 equal parts. So, what I have done is I have bisected the 3 sides into two equal parts, and then I have drawn this triangle inside. And this inner triangle I am going to sort of color it blue. Now, I have three triangles remaining, and what I am going to do is I am going to do exactly the same thing to them. So, I am going to divide each of these triangles into 4 equal parts, and I am going to take the center one and remove it from my set, right. I am going to color it blue, which means it is no longer in contention. And then I could do it to all the remaining triangles once again. So, you see what is happening is, while earlier we were moving from top outwards and downwards, here we start with a bounded triangle and we sort of keep moving inwards. And this is an example of what is called, mathematicians called a fractal. It's, you keep doing this indefinitely. So, you keep removing more and more smaller and smaller triangles, and when you take the intersection of all these sets, you are left with a set called the Sierpinski gasket. Which is an example of a set. It is drawn inside a two-dimensional plane, but its dimension is not quite 2. It is a set of fractional dimension called a fractal. Okay, let us come back to our Pascal's triangle, the odd numbers in Pascal's triangle. I want to now ask that if I were to take some row of Pascal's triangle, let me take for example this row over here. Now, I want to know how many odd entries are there in this row. Okay, more precisely, let us define a n to be the number of k between 0 and n such that n choose k is odd. And so, the question is, what does the sequence a n look like? Can we find a nice formula for a n? Well, let us go back further and look at some examples that we had worked out, see what these values of a n look like. So, here we actually have the first few rows of Pascal's triangle, and let us look at the values of a n. So, I have to just count the number of odd numbers in each row, the number of things in red. So, here I have 1, in the next row I have 2, in the next row I have 2, in the next row I have 4, 2, 4, this is again 4, etc. So, what do you observe here? Well, it's not exactly clear what the pattern is, but what it does look like is that in each row the number of odd entries is some power of 2. We have already seen that if n equals 2 to the k minus 1, then a n is well, all the entries are odd, as we see for example here in n equals, this is the row 0 1 to row with n equals 3. We saw this also in the row n equals 7. So, a n is 2 to the power k, which is equal to n. And we also saw that if n is 2 to the power k, then what happens? Well, this is the row following a row where everything is odd. So, in that row only the two entries at the end are odd, everything in between is even. So, a n is actually 2, that's so this row has 2 to the k plus 1 entries because k goes from 0 to 2 to the k, and all but 2 of them are even, and so we have just a n is just 2, the number of odd entries is 2. So, you see it fluctuates wildly. On the one hand, for 2 to the k minus 1, a n is equal to n, for 2 to the k, a n is equal to 2. So, can we work out some sort of recurrence relation for a n? So, this is going to be a little different from the recurrence relations you have already seen. Let me move back to this big picture. So, if you look at this row a n, this row, the nth row, it looks like it is actually there is this big 0 region in the middle, and it is 2 copies of a row that occurs somewhere a little above it. So, it is actually 2 copies of this row, because what we have here is 2 of the same triangles that we had on top. So, there is some relation between a n and this. So, this row has twice as many odd numbers as the row above. What is the number corresponding to the row above? So, let us see, in this example, this row is over here we have row number 2 to the k minus 1, and then row number 2 to the k. So, you look for the largest power of 2 such that 2 to the k is less than n, and you subtract it from n. This row here, this row number is n minus 2 to the power k, because this distance from here to here is the same as the distance between 2 to the k and n. So, what we have shown is that if we write k to be the largest in power of 2, the largest integer r greater than or equal to 0, such that 2 to the power r is less than or equal to n, then a n is 2 times a n minus 2 to the power k. So, for example, let us look at n equals 47. So, what is the largest power of 2 that is less than 47? Well, think about it. So, you start with 2, 4, 8, 16, 32, and then you get 64. So, 32 is the largest power of 2 that is less than 47, and so we 32 is 2 to the power 5. So, in this case k is equal to 5, 2 to the power 5 is 32 is less than or equal to 47, and 2 to the power 6, which is 64, well, that is greater than 47. So, we have n minus 32, well, what is that? N minus 32 is 15, right. So, what we get is that a 47 is 2 times a 15. And now, what about a 15? Well, we look for the largest power of 2 that is less than 15. What is that? Well, that is 8. So, that is 2 to the power 3, and so we must look at 15 minus 8, which is 7. Then we look for the largest power of 2 that is less than 7, and so we get 2 into 2 into 2 into, so the largest power of 2 that is greater than 7 is 4, and so, and what is left? 7 minus 4 is 3, and so 2 into 2 into 2 into the largest power of 2 that is less than or equal to 3, well, that is 2, and then we are left with A1. But what is A1? Well, A1 is the row with n equals 1, it has 2 entries, right, 1 choose 0 and 1 choose 1, both of which are odd. So, this A1 is itself equal to 2. So, this is 2 into 2 into 2 into 2 into 2, which is 32. So, what we found is that the number of k between 0 and 47 such that 47 choose k is odd, this is equal to 32. There is another nice way of thinking about the value of the sequence a n. It involves the binary expansion of the number n. So, remember what is this when I write a number like 54723, what does this mean, the decimal expansion? Well, what this really means is we have 5 into 10 to the power 4 plus 4 into 10 to the power 3 plus 7 into 10 to the power 2 plus 2 into 10 to the power 1 plus 3 into 10 to the power 0. So, this is the decimal expansion of the number 54723. Similarly, for every natural number n, you can start with this. N can be written as 2 to the power k plus b subscript k minus 1, 2 to the power k minus 1 plus b1 2 to the power 1 plus b0. For unique k greater than or equal to 0 and b0, b1 up to bk minus 1, either 0 or 1. This is the binary expansion. For example, if we take the number 47, its binary expansion is so it's 32 plus, and so then we were left with 15, which is 8 plus 4 plus 2 plus 1. So, this is 2 to the power 5 plus 2 to the power 3 plus 2 squared plus 2 to the power 1 plus 2 to the power 0. This sequence of numbers that we got, so we can write it as 2 to the power 5 plus 0 into 2 to the power 4 plus 1 into 2 to the power 3 plus 1 into 2 squared plus 1 into 2 to the power 1 plus 1 into 2 to the power 0. And we usually say that write this as a binary expansion. The binary expansion is 1 0 1 1 1 1. Now, let us go back and look at how we calculated A of 47. A of 47, well, that is A of 1 0 1 1 1 1, that is 2 into A of 1 1 1 1, which is 4 into A of 1 1 1, which is 8 into A of 1 1, which is 16 into A of 1, which is 32. What we have is that A of 1 0 1 1 1 1 is 2 to the power 5. This 5 here is nothing but the number of times 1 occurs in the binary expansion of 47. So, what we have is that in general, I will write it down as a theorem, A n is equal to the number of times is 2 to the power number of times 1 occurs in the binary expansion of n.